For the final episode of the RADNUC web series, I was joined by Professor Amy Gandy to talk about nuclear fusion. Professor Amy Gandy is Head of Programme on Nuclear Fusion at the UK Atomic Energy Authority. Prior to this, Amy was a Senior Lecturer in Nuclear Materials Engineering at the University of Sheffield, where her research was focused on the development of novel materials for nuclear fusion reactors, encompassing metallic and ceramic materials research. Amy has years of experience working on this exciting frontier in nuclear materials research and has built a wealth of knowledge on the subject of nuclear fusion. Here, Amy shares some of that knowledge with us as she discusses the concept of nuclear fusion, how fusion reactors work, the practicalities of running a fusion reactor, and the future of nuclear fusion.
Hi, Amy.
Hello.
How are you?
I'm good, thank you. How are you?
I'm good, thanks. Thanks for joining us for the final episode of the series on Introduction to Nuclear.
My absolute pleasure.
Yeah, I've been looking forward to this one because I don't know that much about fusion, so it's going to be a learning curve for me as well.
Awesome. Hopefully I can teach you lots of stuff then.
Yeah. I guess we'll start with quite a broad question. At the start of the series, we looked at fission and what fission is. So what is nuclear fusion?
Well, if you know all about fission, then you'll know nuclear fusion is the opposite of fission, essentially. So fission, where you're splitting large particles, so uranium-235, into smaller pieces and releasing your neutrons. Nuclear fusion is the opposite in that you're fusing really small particles together. The fusion reaction that we're going to hopefully achieve on Earth, and we have achieved it in some test reactors, is fusing isotopes of hydrogen together, so deuterium and tritium. And when you fuse them together, they form an alpha particle, so a helium nucleus, and a very energetic fusion neutron. And it's that fusion neutron that has about 14.1 MeV of energy, and fission neutrons are on the order of 2 MeV of energy. It's that fusion neutron that's ultimately going to be used to generate electricity. And because of the energetics of that fusion neutron, it means that fusion has the potential to generate 4 times the amount of energy that fission does.
Wow.
And fission has the potential to, does generate 1 million times more energy than burning coal, fossil fuels. So it will be, if we can achieve it in a commercial sense, a technology that allows us to produce the most amount of energy compared to any other technology we have currently on this Earth.
That's fantastic.
Yeah, very, very exciting. Very difficult to achieve, but worthwhile if we can do it.
Right. Well, that kind of brings me on to my next question, actually, because it's generating, did you say 4 times more than fission?
Yeah.
How can we harness that energy? So I guess as a prerequisite, how do fusion reactors work? What do they look like?
There are different technologies that are being developed for fusion. Arguably the most mature technology is called magnetic confinement fusion. And that's what the UK's commercial fusion program is going to be using. In order to fuse hydrogen isotopes together, so deuterium and tritium, you have to create a plasma of these ions essentially. So you have to heat them to really high temperatures, 150 million degrees Celsius, which is 10 times hotter than the core of the sun. But we can do that. That's a technology that we were already able to achieve. So when you do that, you're stripping away the electrons and you're creating a soup, essentially, so a plasma of charged particles. And because they're charged particles, you can then manipulate them using magnetic fields. So really strong magnetic fields on the order of about 13 Tesla are going to be applied to essentially squish the deuterium and the tritium ions together, confining them into a really small volume or relatively small volume. And that increases the probability that they're going to fuse together. So when they fuse together, like I say, they produce the helium and the neutron. The neutron will fly out of the fusion core and it will go into what is called the breeder blanket. This is the component surrounding the fusion core. And it'll interact with the atoms in that component in lots of different ways. And one of the ways is an inelastic interaction where it will lose energy in the form of heat. And that heat then will be removed using some coolant channels and then used to boil water, to generate steam, to turn a turbine, generate electricity. So that is exactly the same technology as in current fission power stations and fossil fuel burning power stations. It's just the generation of the heat that is going to be different. So in a PWR, for example, there are inelastic interactions between the neutrons and the water, heating up the water, and that heat is then transferred. Here in a magnetic confinement fusion device, it's the inelastic collisions with the materials in the breeder blanket. They're going to generate heat, and that's what we're going to remove to ultimately generate electricity. So that's how it will hopefully work if we can get all of these components operating together.
Right. Okay. And the breeder blanket is obviously in the solid state. Is there
Sure.
a water circuit in contact with the breeder blanket?
So remember, all of the concepts that I'm talking about are still under development. There is no working nuclear fusion power station. Everything that we're doing at the moment in the fusion space, they're still experimental devices. So the actual coolant system itself is still under development. So what that actually looks like, still completely still somewhat unknown unless you're working in that area. But yeah, the idea is there'll be some form of cooling channels and water potentially, maybe some other substance, and the heat will transfer from the material in the breeder blanket through the coolant channel materials into the coolant channel material itself, and that will then be removed. Whilst a lot of the materials in the breeder blanket will be in the solid state, the breeder blanket's other purpose is to breed fuel. That's why it's called a breeder blanket. So to produce one of the fuel sources for fusion. So deuterium is a stable isotope. You can produce it from seawater. Tritium, however, has a half-life of about 12.3 years. So it's a radioactive isotope, and there's actually very little of it on this planet. So for a sustainable fusion power station, we actually have to produce our own tritium in the breeder blanket, so in the region surrounding the core of the fusion device. And that's probably going to be a source of lithium, because the fusion neutron can be absorbed by the lithium, and then that lithium will transform, it will transmutate into tritium, which is a gas, and hydrogen, helium, another gas. And via some other technological process still under development, that tritium will be extracted from the breeder material and put back into the core of the fusion reactor, so producing a self-sustaining fusion reaction. So there are two main concepts for that breeder blanket material: solid ceramic materials, lithium metatitanate, orthosilicates, lots of other ceramic materials, or liquid lithium or liquid lithium lead eutectic, or some combination of other elements as well. The material challenges, depending on which material you're going to go with, are obviously very different. Having a liquid lithium lead material in another material in a radiation environment at high temperatures under magnetic fields is obviously a very challenging environment, but you get a really high lithium density, so it's a more sustainable source of fuel. You'll be able to breed the amount of tritium that you want to breed. The lithium ceramics that people are working on has a lower lithium content, so therefore we have to do clever things by adding in neutron multipliers, so increasing the number of neutrons that are going to be produced. So there are still a lot of material challenges and a lot of unknowns when it comes to the actual breeder material itself. But the idea is it'll breed tritium, and it will also remove the heat that is generated from the other interactions with the neutrons, and that will be used to generate electricity.
And I guess how we harvest the tritium gas is also not currently...
Yeah. So if you want to have a career in a nuclear technology, fusion is probably one of the ways to go, because there are still so many things that are currently being developed. What we can do is we can produce the fusion plasma, we can fuse deuterium and tritium together. So the Joint European Torus down at Oxford, JET, was the first to fuse deuterium and tritium together, the actual fuel. And the amount of energy they got out was exactly what the computational model suggested they would do, which is what gives us confidence that we are going to be able to generate more energy out than we put in, because at the moment we have to put a lot of energy in to fuse these things together. The next version, but JET's still an experimental test device. ITER, which is 10 times the size of JET, is hopefully going to be demonstrating that we can get more energy out than we put in. At least we can break even. That's currently under construction down in France, and that's an international collaborative project. In addition to that, though, there's lots of other fusion test facilities around the world that are also testing different components, whether it's the different isotopes of hydrogen. So some are doing deuterium, for example, the different materials, the different breeder concepts. There's a huge resurgence, a huge increase in the amount of experiments that are being undertaken across the world, looking at things like the different breeder materials. So looking at liquid lithium, for example. There are lots of people now looking at improving the superconducting magnets, because that's what we're going to be using, but they can readily lose their superconductivity when they become damaged because of the fusion neutrons. So it's how can we improve that? So there's an awful lot of work going on at the moment, and we don't yet at the moment have a test fusion power station that we can really test all these things in. ITER is going to be potentially the first one. The UK has their own commercial fusion program, STEP, the spherical tokamak for energy production, and that's hoping to come online in early 2040s, and that's hoping to demonstrate that we can actually generate electricity from fusion. And within STEP, we will be able to test out different systems as well. So there's an awful lot of work to be done. It's a really exciting time for fusion. I think we're still plasma physics that needs to be done, but we're really now moving into the engineering and the technology and the material science and aspect of it to really, and the supply chain as well of the materials, to really start to build an actual working fusion power station. So yeah, a really exciting time.
It is. You brought up a lot of things there, lots of areas of research, and I've got questions about everything. This really deserves a series to itself, fusion, because there is. I
agree.
There's so much going on. But you see in the news quite often that at one of these experimental reactors you're talking about has managed to sustain the fusion reaction for a minute or something like that. Is sustaining the plasma one of the biggest challenges, and why is it? What's stopping the reaction from just continuing?
Yeah, that's an awesome question. And it's going back to the magnets that I was talking about before. So JET, for example, uses traditional electromagnets, so made out of copper, and they can only operate for, don't quote me, but on the order of 5 minutes, for example, before they overheat. So that's what has always been the limitation in the length of time that we can sustain a plasma for a jet. And it'll be similar issues around the world, which is why superconducting magnets are being developed so that we can sustain a plasma for a longer period of time. Having said that, a lot of the fusion devices are being developed to operate on a pulsed plasma anyway. So it's not about sustaining plasma for years at a time. Actually, the technology is being developed so that we can utilize a pulsed plasma rather than a very long duration sustained plasma. The other records that you were talking about in other countries, they weren't using deuterium and tritium, they were using deuterium and deuterium, and that's not going to produce the amount of energy required to be able to produce electricity ultimately. Again, it's a test reactor, it's testing their magnets and their components. Can we actually sustain a plasma for long durations? And if we can, then we'll use the actual fuel later on. Because of the issues I said with tritium earlier on, it's really scarce and it's radioactive. So by creating a fusion plasma that's very similar in a not an active way is the way all countries have been going in order to test a lot of their other systems. So it's basically the limitations in the magnets that we have at the moment.
Okay, yeah, and you said, sorry, deuterium and deuterium doesn't generate as much energy as deuterium tritium.
No, don't quote me again. I think it's the energy of the neutron that's produced isn't as energetic, and therefore the amount of energy ultimately that can be transferred from that neutron to the materials that can then be used to produce heat is going to be less.
Yeah.
Is my understanding.
Okay.
You may want to cut that.
Got you. Sorry, I'll just take a look at my notes. I've got loads written down and I have to be selective about what I pick. Sure. Again, I don't want to keep you here all day.
That's fine.
But I've got written down danger ?
Yeah.
So again, you see a lot of headlines saying they've fired up a quote unquote artificial sun on Earth. How dangerous is a fusion reactor?
Yeah, I love it. We are creating a sun in the box and it sounds awesome and it is amazing. But I also understand that does sound a bit scary as well. Because it's so difficult to achieve fusion, high temperatures, magnetic fields, that confinement. So the shape of the fusion core is really important as well. As soon as anything happens, so if the electricity is switched off, the power's switched off, the plasma just dissipates. The magnets are confining the plasma so that the materials that are closest to the plasma never experience those intense temperatures, and that temperature dissipates relatively quickly in the event of a shutdown. So the materials that we're developing to operate up to about 1300 degrees Celsius. So now we're in manageable terms for material science and engineering. So if there was a shutdown, if all the electricity went off, then the fusion process would just stop. So no neutrons would be produced.
Yeah.
And the fuel that we're using is only the tritium that's radioactive. And as I said before, it's got a half-life of 12.3 years. It's a beta emitter. And the amount we use is tiny. So at the moment, jet uses like a teaspoon every time it's firing up. So
Wow.
very small amounts.
Yeah.
And there will still be containment. There's still shields. You know, we know how to contain radioactive material from nuclear fission, but it's very, very different from those alpha-emitting, long-lived radionuclides that we have to deal with and we deal so well with in nuclear fission. We don't have the same challenges for nuclear fusion. So that's one of the reasons that people say it's a safer alternative. I mean, there are always risks associated with any technology, but the amount of radioactive material in a fusion device at any one time is tiny. Also, those fusion neutrons, they can make materials radioactive. It's not so much as an issue in nuclear fission because of the energy of those the neutrons that produce, but because they're so energetic, common elements that we would normally have in steel, molybdenum, for example, cobalt, nickel, they will absorb a fusion neutron and they can transform into quite radioactive materials during the decay chain and produce a lot of alpha particles and or protons, so hydrogen and helium. So the other thing we do have to consider is we can't just say, oh, there's no long-lived radioactive waste produced in nuclear fusion. Okay, yeah, we're not using the actinides, we're not using uranium, plutonium, generating things like that. But the materials that we build our fusion power station out of can become radioactive and will become radioactive because of the interactions with the fusion neutron. So what we have to do is choose materials that are not going to be active for significant periods of time. Okay. 100, 1,000 years, for example, and also are considered low level or intermediate level waste.
Right.
So this is a challenge for us now working on developing materials for fusion. Not only do they have to perform in this really extreme environment in terms of temperature and radiation, but we've also got to choose materials that are what we call reduced activation. So it's really key to know that whilst it's a relatively safe technology in terms of we can't have a runaway, there's no meltdown, for example, we can't have a runaway chain reaction, we do have to be really clear and honest that waste is going to be generated. It's just going to be different waste or intermediate or low level waste. So it's not going to be the same high level radioactive waste that we have to deal with in nuclear fission.
Yeah.
So yeah, so they're the main things that we have to be really clear and you know, communicate that to the communities. It is a safe technology, inherently safe technology, but we will still generate waste, but it is going to be a different type of waste in nuclear fission.
Brilliant. Yeah, you've actually answered my next question actually about waste. So.
Yeah, they always come hand in hand.
Yeah,
so.
Yeah, absolutely. It's a huge advantage because one of the biggest challenges with fission is, of course, the high level waste you generate.
Exactly.
Awesome.
Yeah.
I've asked about fuel. So fuel, we need tritium and deuterium.
Uh-huh.
And that comes from electrolysis of seawater.
So deuterium is a process that is already at an industrial scale because you can produce deuterium for things like NMR machines and other industrial applications. The precise mechanism, I must admit, I don't know. I think it is an electrolysis type process. As I said, to produce tritium, we have to breed it using lithium.
Yeah.
Lithium is a relatively abundant material on Earth. We have to also look at the supply chain of lithium. Which countries are we going to get it from? What are the geopolitical issues that we have to consider? But I'm going to quote the CEO of UKAEA here. The amount of lithium that we need is predicted to be needed per fusion device per year is the same as the amount of lithium in 2 laptop batteries.
Wow.
I know. So it's a tiny amount.
Yeah.
Because of course we will be competing with energy storage, so batteries, the battery technologies for lithium. But the amount of lithium we need is minimal.
It is. That's minuscule. That's
and
unbelievable.
He also said that the amount of deuterium we need is the same as per year, the same as filling a bathtub full of water.
Wow.
I know. Incredible.
That's
Which
incredible.
is why we're saying it's a really sustainable source of energy.
Yeah,
because of the
absolutely.
amount of fuel that you actually need.
I didn't know that at all. When I heard the electrolysis of seawater thing, I thought you're going to need massive cubic meters of seawater and the amount of electricity it would consume, but that is really a small amount.
I knew it was small, but it wasn't until he said that how small it was going to be. Yeah,
that's fantastic.
Amazing.
Okay. one of my questions here is, what are the biggest challenges in the way of commercial fusion? So we touched on some of the technical aspects. Is there anything, I'm guessing policy is not quite caught up with the technology yet. Is there anything from the regulatory or policy aspect that's standing in the way of commercial fusion?
Well, commercial fusion is going to be, as I understand it, managed by the Environmental Agency and HSE, rather than having to be managed in the same way that nuclear fission is. One of the big issues that we have is qualifying new materials to be used in nuclear fusion, because that takes an awful long time, basically just to demonstrate the safety case. This thing can actually operate in these conditions for this period of time as we predict it's going to be, because we don't have a nuclear fusion device to test any of our materials yet. So we have to wait until we have fusion to test. So we have to use a wide range of other methods in order to test our materials and our components. So qualification of materials and qualification of components is a challenge, and that's just an ongoing challenge, and that's just one that we have to accept and work towards. So in terms of standing in the way of commercial fusion, actually the UK government have committed an awful lot of money to developing our own commercial fusion power stations. We've already got a site, so it went out to public consultation last year, or the year before last, and it's been now agreed that we're going to place it at West Burton. Gosh, my mind, you might want to cut that out because I've forgotten where it's going to be.
Okay.
That's terrible. But yeah, so we've already got a site agreed within the UK as to where that fusion device is going to be built. And there's an awful lot of funding out there with academia and industry and government labs as well to basically ensure that we can construct that fusion device by the early 2040s, which is when STEP's hopefully going to be turning on by. And it's not just in the UK, there's commercial fusion programs all around the world. The US recently announced that they wanted to commit hundreds of millions of dollars to develop their own commercial fusion power station as well. So historically, because I guess people couldn't demonstrate the maturity of the technology, it was always a fusion experiment. But now, because of the records that are being broken, and because of the advancements that JET and MASS, which is the spherical tokamak down at Culham, that they've made, the government, UK government and the global communities are now more confident that we can achieve fusion, and therefore we are being given more money in order to do so. So there's no real barrier to doing that anymore. The commercial programs have started and they're ongoing, and that we're working with lots of industrial partners. There are so many industrial startups that have been formed here and in other countries. General Fusion is a Canadian company, for example. They're building their test devices down in Abingdon. You've got First Light, Tokamak Energy. All of these other companies are also trying to develop commercial fusion. So there's an awful lot of people now doing it. Like I said earlier, it's just a really exciting time to be involved in fusion.
It is. It's good to see that everyone seems to be pushing it forward.
Yeah.
There's a lot of regulatory things in the way of, or were in the way of fission, and it makes sense looking at the technical aspect why fusion seems a lot safer, and probably wouldn't have the same sort of regulatory.
Yeah, exactly. As we were talking about before, the regulatory considerations are different because it is a different technology, and the waste streams are going to be different. But we need to identify what those waste streams are, so we know what is the waste management and disposal routes, and these are ongoing research programs as well. Yeah.
Brilliant. Good. One final question. How did you get into your area of research, and what is your favourite aspect of your research?
I have been working on radiation effects in materials since 2003. I was working on understanding helium bubble formation in semiconductor materials for my master's project, and that led on to my PhD using electron microscopy and ion implantation. And I've just been in the area ever since, basically. So as I said before, we don't have a working fusion device to test any of our new materials. We have to use other methods, and one of those methods is ion implantation. So unbeknownst to me at the time, when I was working on semiconductor materials, so very different, I would be using exactly the same technologies and ion implantation, exactly the same characterization methods 20 years later to develop materials. Initially, it was for fission when I first joined Sheffield in 2011, and now for fusion. I've always just been absolutely fascinated with how particulate radiation changes materials at the nanoscale and microscale, and then ultimately how that changes the properties. As a physicist, I hadn't realised that what I was doing was actually material science. It wasn't until I came to the material science department here that I realised, that is what I've been doing for the last X amount of years. So yeah, I kind of fell into it by accident, and have never left because it's just an absolutely fascinating area. And it's an area that I can apply to a wide range of different materials. So for fusion, for example, we're developing the fuel, which is in our case the ceramic fuel, but also the first wall. So these are the materials that are closest to the fusion plasma. So the materials that will arguably experience the most extreme environment on Earth. And they're typically metallics, so metal alloys. So very different, but the same approach can be used to investigate both types of materials. And so, yeah, what's the most interesting or most exciting part of my job? Wow. Working with lots of people, because we can't achieve fusion or any big engineering challenge by using one person or one type of one area of research. I work with so many amazing people, not only this department, across the faculty, across the university, and across the world. And we're working together in such a wonderfully collaborative way that we're able to kind of make strides in materials and science and engineering, and so developing these new concepts. And seeing people grow and develop in that area as well. That's just really, I love all of that. Basically, it's like we're one big happy family, kind of working together. I know that sounds really trite, I guess is the word, but it genuinely is true. Yeah.
No, that's amazing. And the way you described it, seeing the most extreme environments on Earth, it is such an interesting and cool frontier in material science and engineering.
Yeah, it absolutely is. We can learn lessons from nuclear fission, absolutely, but the amount of radiation that's going to be generated in the core of a fusion device is an order of magnitude greater. The amount of helium and hydrogen that's going to be generated inside materials due to transmutations are going to be an orders of magnitude greater. Obviously, the temperatures are a lot higher than current nuclear fission reactors. We've got the magnetic field actually exerting stress on our materials. And then we have to work out a way of getting the heat out from the material, of generating the fuel, the tritium. I mean, it's just a fascinating challenge. It's super difficult, but yeah, it's just a really interesting area to be working in.
Brilliant. You've got me interested in joining the field as well.
You should.
All right. Thank you so much, Amy. I've learned so much.
Excellent. Good.
And I hope the viewers agree too.
Yes, I hope so.
Thanks, Amy. Thanks very much.
Cheers.